Long before chemistry, before planets, before life could even be imagined, the universe was already making a quiet decision about what kind of reality it would allow. In the first moments after the Big Bang, matter existed in a raw, unstable form, a seething ocean of energy where particles appeared and vanished almost instantly. Protons formed early, carrying positive charge, eager to repel one another. Electrons followed, light and restless, orbiting wherever attraction allowed. Yet this charged world alone could not build complexity. If reality had stopped there, the universe would have been little more than a thin fog of hydrogen, simple, fragile, and limited. What changed everything was the arrival and persistence of a particle that did not announce itself with charge or light. A particle that did not push or pull electrically, but instead settled quietly into the very center of matter. That particle was the neutron. The neutron can be understood as the silent architect of matter, because it determines whether atoms can exist beyond the simplest form. At the core of every atom heavier than hydrogen, neutrons occupy the nucleus alongside protons. Their presence is not decorative or optional, it is structural. Protons, all carrying the same positive charge, naturally repel each other. Pack them together without restraint, and the nucleus would tear itself apart. The neutron enters this hostile environment without adding to the electrical conflict. It carries no charge, yet it participates fully in the strong nuclear force, the most powerful binding force known in nature. By doing so, it allows protons to remain close enough to form stable nuclei. Without neutrons, matter would be shallow and repetitive. With them, matter becomes layered, diverse, and capable of endless variation. This role is often misunderstood because the neutron does not behave like a traditional stabilizer in everyday experience. In human terms, stability usually comes from rigidity or resistance. The neutron, by contrast, stabilizes through neutrality. It does not counter protons by opposing them electrically. Instead, it complements them by adding mass and strong, force interaction without increasing repulsion. This subtle balance is what makes it so powerful. The neutron does not dominate the nucleus, it harmonizes it. Every stable element in the periodic table reflects a precise neutron-to-proton ratio, a quiet numerical balance that determines whether an atom will exist peacefully or decay violently. As elements grow heavier, the importance of neutrons increases dramatically. Light atoms like helium can exist with relatively few neutrons, but as proton numbers rise, more neutrons are required to offset the growing electrical repulsion. This is not a coincidence. It is a structural necessity. The architecture of matter demands more neutral support as positive charge accumulates. When this balance is achieved, atoms can persist for billions of years. When it fails, atoms become radioactive, unstable, or short-lived. In this way, neutrons do not merely support matter, they define its limits. The neutron's architectural influence extends beyond individual atoms into the formation of elements themselves. Inside stars, under extreme temperatures and pressures, nuclear reactions fuse lighter nuclei into heavier ones. Neutrons play a crucial role in these processes because they can enter atomic nuclei without being repelled by electric charge. A proton approaching a nucleus must overcome electrical resistance, but a neutron encounters no such barrier. This makes neutron capture one of the primary pathways by which elements grow heavier in stellar environments. Through slow and rapid neutron capture processes, stars manufacture the elements that later become planets, oceans, mountains, and living organisms. The iron in blood, the calcium in bones, and the gold in jewelry all owe their existence to ancient neutron interactions in dying stars. What makes this even more remarkable is that neutrons themselves are not inherently stable outside the nucleus. A free neutron decays within minutes into a proton, an electron, and a neutrino. This instability reveals a deeper truth. The neutron's true identity is relational. It is stable not because it exists alone, but because it exists in the right environment. Inside the nucleus, bound by the strong force, it becomes a cornerstone of matter. Outside, it transforms. This tells us that the architecture of reality is not built from isolated components, but from relationships and conditions. The neutron exemplifies this principle perfectly. It is not powerful by itself. It is powerful because of where it belongs. The silent nature of the neutron's influence also shapes how matter interacts with time. Stable nuclei persist across cosmic history, allowing atoms formed in ancient stars to remain intact across billions of years. This persistence is essential for the continuity of the universe. Without long-lived atoms, there could be no geological history, no biological evolution, no memory written into matter itself. The neutron, by enabling nuclear stability, allows time to leave its mark on physical structures. Rocks remember pressure, fossils remember life, and atoms remember their origins. All of this is possible because the neutron holds nuclei together quietly, patiently, across unimaginable spans of time. The neutron also determines the identity of elements through isotopes. Atoms of the same element can have different numbers of neutrons, leading to variations that are chemically similar but physically distinct. Some isotopes are stable, others radioactive. This subtle variation has enormous consequences. Radioactive isotopes heat the interiors of planets, drive geological activity, and provide clocks that allow scientists to measure the age of the Earth and the universe. Medical imaging, cancer treatments, and archaeological dating all rely on the predictable behavior of neutron, rich or neutron, deficient nuclei. Once again, the neutron operates behind the scenes, shaping outcomes without drawing attention to itself. Even at the boundaries of matter's existence, the neutron defines what is possible. In the most extreme environments known, such as the cores of massive stars, gravity becomes so intense that atoms collapse. Electrons are forced into protons, forming neutrons. The result is a neutron-dominated state of matter so dense that ordinary atomic structure disappears. What remains is supported almost entirely by neutron interactions. In these conditions, the neutron is no longer just an architectural component of atoms. It becomes the architecture itself. Neutron, rich matter resists further collapse, setting the stage for neutron stars, objects that challenge our understanding of physics. These stars demonstrate that the neutron's stabilizing role scales from the microscopic to the cosmic. The paradox of the neutron as an architect lies in its invisibility. We are naturally drawn to what we can see, measure easily, or feel directly. Electric charge produces sparks, currents, and light. Mass produces weight and gravity. The neutron produces none of these sensations directly. It leaves no trail of charge, no glow of radiation unless it decays or interacts strongly. Yet remove it, and the entire structure of matter collapses into simplicity. The neutron teaches a profound lesson about power. The most important forces are often the least visible. In documentary terms, the neutron's story is not one of dramatic action, but of persistent influence. It does not explode into existence or dominate attention. It occupies the center, performs its role, and allows everything else to happen. This makes it easy to overlook and difficult to appreciate. Yet every physical object, from the smallest grain of sand to the largest planet, carries the signature of neutron architecture within its atoms. The solidity of matter, the diversity of elements, and the stability of the physical world all trace back to this neutral particle. To call the neutron the silent architect of matter is not poetic exaggeration. It is a precise description of its function. Architects do not live inside the buildings they design, nor do they announce their presence in every room. Their influence is seen in structure, balance, and endurance. In the same way, the neutron does not reveal itself through charge or light. Its influence is seen in the fact that matter holds together at all. Without it, the universe would be a vastly simpler, poorer place, incapable of complexity or life. In the end, the neutron reminds us that reality is not built by noise and force alone. It is built by balance, restraint, and silent cooperation. The neutron stands at the core of matter, uncharged, unseen, and indispensable, shaping the universe not by what it does loudly, but by what it allows to exist. Power is often misunderstood because we associate it with visibility. We believe something is powerful if it shines brightly, moves violently, or announces its presence through force. Electricity crackles, magnets pull, gravity bends space, and light floods the universe with information. Against this backdrop, the neutron appears almost irrelevant. It carries no electric charge, produces no glow, and passes silently through matter that would stop other particles. Yet this very neutrality is what gives the neutron its extraordinary influence. The second keynote rests on this paradox. The absence of charge is not a limitation, but the source of the neutron's hidden power. To understand this, one must first appreciate how deeply electric charge dominates ordinary matter. Almost every interaction we experience in daily life is electromagnetic in nature. The solidity of objects, the friction between surfaces, the flow of electricity, and even the chemistry of life itself arise from the attraction and repulsion of charged particles. Protons and electrons dictate how atoms bond, how molecules form, and how energy moves. In such a universe, anything without charge seems like an outsider, disconnected from the main story. But the neutron operates beneath this visible layer, influencing the rules rather than the outcomes. Inside the atomic nucleus, neutrality becomes a strategic advantage. Protons repel each other strongly due to their positive charge. As more protons are packed into a nucleus, this repulsion grows rapidly, threatening to tear the nucleus apart. If neutrons carried charge, they would only add to this instability. Instead, their neutrality allows them to slip into the nucleus without increasing electrical tension. Once inside, they participate fully in the strong nuclear force, binding protons together at distances where no other force can compete. This combination, electrical neutrality paired with strong force participation, is what makes neutrons uniquely effective. They can enter where charged particles struggle and stabilize what would otherwise collapse. This influence becomes more pronounced as atoms grow heavier. In light elements, the balance between protons and neutrons is relatively simple, but in heavy elements, neutrality becomes essential. The increasing number of protons creates intense repulsive forces that would overwhelm the nucleus without sufficient neutron support. Neutrons act as buffers, spacing protons in a way that allows the strong force to dominate over electrical repulsion. In doing so, they quietly set the upper limits of atomic stability. When there are too few neutrons, nuclei become fragile and decay. When there are too many, they become unstable in a different way. The neutron's power lies in maintaining a narrow window of balance, a hidden influence that determines whether an element can exist at all. Neutrality also gives neutrons an extraordinary ability to move through matter. Charged particles interact constantly with electrons and nuclei, losing energy and changing direction. Neutrons, lacking charge, are not easily deflected. They can penetrate deep into materials, passing through layers that would stop protons or electrons almost immediately. This property makes neutrons both elusive and invaluable. In scientific research, neutron beams are used to probe the internal structure of materials, revealing arrangements of atoms and magnetic properties that cannot be seen with other forms of radiation. In these cases, the neutron's lack of charge is not an obstacle. It is precisely what allows it to reveal hidden structures. This same neutrality is what gives neutrons their transformative role in nuclear reactions. In nuclear fission, a neutron enters a heavy nucleus without facing electrical resistance. Its arrival destabilizes the nucleus, causing it to split and release energy along with additional neutrons. Those neutrons, in turn, can trigger further reactions. The entire process hinges on the neutron's ability to approach and enter the nucleus freely. A charged particle would be repelled long before it could have such an effect. Here, neutrality becomes the key that unlocks immense energy. The neutron does not supply the energy directly. It simply initiates the process. Yet without it, the energy would remain locked inside the nucleus. In nuclear fusion, neutrality plays a subtler but equally important role. While fusion primarily involves charged nuclei overcoming repulsion at extreme temperatures, neutrons often emerge as products of these reactions. Once released, they carry energy away from the reaction zone without being trapped by electromagnetic forces. This ability to transport energy efficiently is crucial in both stellar processes and experimental fusion reactors. In stars, neutrons help redistribute energy and contribute to the complex chain of reactions that sustain stellar life cycles. Again, their lack of charge allows them to act freely where charged particles are constrained. The neutron's neutrality also shapes the way matter evolves over time. Radioactive decay often involves changes in neutron number rather than proton number. When a nucleus has too many neutrons, one can transform into a proton, emitting an electron and a neutrino. This process subtly alters the identity of the atom while preserving overall charge balance. Through countless such decays, matter gradually moves toward stability. This slow evolution of elements is essential for the long-term behavior of the universe. Planets cool, stars age, and radiation backgrounds change, all influenced by the quiet reshuffling of neutrons inside nuclei. The neutron does not force change violently, it guides it patiently. In extreme environments, the power of neutrality becomes even more apparent. Consider regions of space filled with intense radiation, magnetic fields, and charged particles. In such places, charged matter is easily deflected, accelerated, or stripped apart. Neutrons, by contrast, travel in straight lines, unaffected by electric or magnetic fields. This allows them to carry information and energy across hostile environments. Astrophysicists detect neutrons from cosmic sources to study processes that would otherwise be hidden. Once again, neutrality grants access where charge would be a liability. The ultimate expression of this principle appears in neutron, rich matter under extreme gravity. In the collapse of massive stars, electrons are forced into protons, creating vast numbers of neutrons. What remains is matter stripped almost entirely of charge. In this state, electromagnetic forces fade into irrelevance, and neutron interactions dominate. The resulting object, supported by neutron pressure and the strong force, resists further collapse. This demonstrates a profound truth. When charge is removed, other forms of power emerge. The neutron's neutrality allows matter to reach states impossible for charged systems. From a broader perspective, the neutron challenges human intuition about influence. We are conditioned to notice what interacts directly with us. Electric shocks, bright light, and mechanical force all command attention. The neutron interacts weakly with our senses and instruments, making it easy to overlook. Yet its influence is woven into the fabric of reality. Every stable structure in the physical world, from atoms to planets, depends on the delicate balance neutrons provide. Their neutrality allows them to operate at a foundational level, shaping outcomes without participating in surface interactions. In documentary terms, the neutron's story is one of understated authority. It does not dominate the visible universe, yet it defines its rules. It does not compete with charged particles for attention, yet it determines whether their interactions can even occur within stable matter. Neutrality, in this context, is not emptiness. It is freedom from distraction, freedom from interference, and freedom to operate where others cannot. The neutron teaches a deeper lesson about power itself. True influence does not always announce itself. Sometimes it is the ability to move unnoticed, to enter forbidden spaces, and to stabilize chaos without being seen. By lacking charge, the neutron escapes the constant push and pull that governs the rest of matter. This escape allows it to become the quiet regulator of atomic structure, nuclear energy, and cosmic evolution. When we say the neutron has hidden influence, we are not speaking metaphorically. Its neutrality gives it access, stability, and reach that charged particles can never achieve. It shapes matter from the inside out, determines the fate of atoms and stars, and enables energies that can warm cities or destroy them. All of this arises not despite its lack of charge, but because of it. In a universe obsessed with attraction and repulsion, the neutron proves that sometimes the most powerful position is to stand neutral at the center of everything. Energy is often imagined as something active and obvious, something that moves, heats, or explodes. When people think of power, they picture flames, engines, or lightning tearing through the sky. Yet the deepest and most consequential forms of energy are often locked away, invisible and silent, waiting for the right conditions to be released. The neutron sits at the center of this hidden world of energy, governing both the stability of matter and the sudden, catastrophic ways that stability can be broken. The third keynote explores this dual role, how the neutron supports order and, under different circumstances, becomes the trigger for immense destruction. At the most basic level, neutrons are responsible for whether atomic nuclei remain intact or fall apart. Inside the nucleus, energy is stored in the bonds created by the strong nuclear force. This energy is not accessible in everyday chemical reactions, which involve only electrons and outer atomic structures. Nuclear energy is millions of times more concentrated because it comes from rearranging the very core of matter. Neutrons are central to this process because they are the particles most directly involved in binding nuclei together. Their presence determines how tightly the nucleus is held and how much energy is stored within it. When a nucleus is stable, neutrons contribute to a balance that locks energy safely away. The nucleus becomes a sealed container, holding enormous potential energy without releasing it. This stability is essential for the existence of matter over long periods of time. Without it, atoms would constantly break apart, releasing radiation and heat uncontrollably. Life, planets, and even stars depend on long-lived nuclei that can store energy without sudden release. In this sense, the neutron is a guardian of stability, preventing the universe from dissolving into constant chaos. Yet stability is not absolute. Under the right conditions, the same neutrons that preserve nuclear order can destabilize it. In heavy elements, nuclei exist in a delicate balance between the attractive strong force and the repulsive electric force between protons. These nuclei are stable only because neutrons provide sufficient binding. When that balance is disturbed, energy can be released with astonishing intensity. A single neutron entering a heavy nucleus can be enough to tip the scales. Because it carries no charge, it can penetrate the nucleus easily. Once inside, it adds energy and disrupts the internal arrangement, causing the nucleus to split. This process, known as nuclear fission, releases energy in two forms: the kinetic energy of the fragments and the radiation emitted during the split. It also releases additional neutrons, which can go on to trigger further fissions. What begins as one quiet interaction becomes a chain reaction capable of producing vast amounts of energy in a fraction of a second. The neutron does not explode or burn, it simply arrives. The destruction that follows is not caused by the neutron's force, but by the energy already stored within the nucleus. The neutron's role is to unlock that energy. This same principle underlies nuclear power generation. In controlled environments, neutrons are used to sustain a steady chain reaction that releases energy slowly enough to be harnessed for electricity. The difference between a power plant and a weapon is not the neutron itself, but the conditions under which neutron interactions occur. In both cases, the neutron is the key that opens the door to nuclear energy. It can warm homes and power hospitals, or it can level cities. This duality highlights the neutron's immense responsibility in human hands. It is not inherently destructive, but it makes destruction possible. The neutron's influence on energy extends beyond fission into the realm of nuclear decay. Radioactive elements emit energy as they move toward more stable configurations. Often, this involves changes in neutron number. When a nucleus has too many neutrons, it may undergo beta decay, converting a neutron into a proton and releasing energy in the form of radiation. This slow release of energy shapes the thermal history of planets, providing heat that drives geological processes such as volcanism and plate tectonics. The warmth of Earth's interior, which sustains its magnetic field and dynamic surface, is partly a gift of neutron-related decay processes. In stars, the neutron plays a similarly complex role. Nuclear fusion, which powers stars, primarily involves protons overcoming electrical repulsion at extreme temperatures. Yet neutrons are produced in many fusion reactions and influence how energy flows within the star. Because neutrons are not trapped by electromagnetic forces, they can carry energy away from dense cores, contributing to the star's energy balance. In supernova explosions, vast numbers of neutrons are released, driving rapid nuclear reactions that synthesize heavy elements. The energy of these explosions, some of the most powerful events in the universe, is deeply tied to neutron behavior under extreme conditions. The concept of infinite power associated with the neutron is not about limitless energy in a single particle. Rather, it reflects the neutron's ability to access and release energy stored on the deepest level of matter. The amount of energy locked inside atomic nuclei is enormous compared to chemical bonds. A tiny amount of nuclear fuel can release energy equivalent to vast quantities of fossil fuels. The neutron makes this possible by acting as the intermediary between stability and release. It stands at the threshold, capable of maintaining order or initiating transformation. This threshold role becomes especially clear in the study of criticality. A nuclear system becomes critical when each fission event releases, on average, one neutron that causes another fission. Below this level, the reaction dies out. Above it, the reaction grows exponentially. The neutron is the variable that determines which side of this boundary the system occupies. Slight changes in neutron number, speed, or absorption can mean the difference between calm stability and runaway energy release. This sensitivity underscores the neutron's power not through magnitude, but through control. Beyond human technology, the neutron's role in energy shapes cosmic evolution. The formation of neutron stars represents an extreme concentration of energy and matter. When a massive star collapses, gravity compresses matter until protons and electrons combine into neutrons. The resulting object stores enormous gravitational and nuclear energy. Neutron stars rotate rapidly, emit intense radiation, and generate magnetic fields trillions of times stronger than Earth's. These phenomena arise because neutrons can exist in states of density and energy inaccessible to ordinary matter. Once again, the neutron is at the heart of an extraordinary release of power. Even the potential for future energy technologies depends on neutrons. Advanced reactor designs, fusion research, and studies of neutron-rich fuels all revolve around controlling neutron behavior. The challenge is not creating neutrons, but guiding them precisely, ensuring that their interactions release energy at the desired rate. This pursuit reflects a broader truth about power. The greatest energies are not those that are unleashed recklessly, but those that are understood and directed carefully. In a documentary sense, the neutron's story is a study in contrast. It is a particle associated with both creation and destruction, with warmth and devastation, with stability and collapse. It does not choose these outcomes, it enables them. The same neutron that helps hold an atom together can also help tear it apart under different circumstances. This dual nature is what gives the neutron its reputation for infinite power, not because it contains infinite energy, but because it grants access to energy scales that dwarf human intuition. Ultimately, the neutron reminds us that power is not always about forceful action. Sometimes it is about position. By existing at the core of matter, neutral and unassuming, the neutron occupies the most influential position imaginable. It stands between order and chaos, between stored energy and released energy. Whether the result is stability that lasts billions of years or destruction that unfolds in seconds depends on how that position is disturbed. In understanding the neutron's role in energy and stability, we gain insight into the deepest mechanisms of the universe. We see how matter can be both enduring and fragile, how enormous power can remain hidden, and how a single, neutral particle can determine the fate of atoms, stars, and civilizations. Every major shift in human understanding begins when a familiar picture of reality quietly breaks apart. For centuries, matter was imagined as solid, indivisible, and permanent. Atoms were thought to be the smallest possible units, eternal and unchanging. That illusion dissolved when science uncovered the inner structure of atoms, revealing a dynamic world of particles, forces, and delicate balances. Among these discoveries, the neutron stands out not just as another component of matter, but as a key that forces us to rethink what the universe truly is. Understanding the neutron does not simply add a detail to physics, it reshapes our entire view of reality. At first glance, the neutron appears almost disappointing. It has no electric charge, no dramatic interaction with light, and no obvious role in everyday experience. Yet this simplicity is deceptive. The neutron exposes the limits of our sensory-based intuition. Human perception evolved to respond to electromagnetic phenomena because they dominate the macroscopic world. The neutron operates beyond that layer, reminding us that the most fundamental structures of existence are governed by forces and interactions we cannot directly feel. By studying the neutron, we are forced to accept that reality is far richer and stranger than our instincts suggest. One of the most profound ways the neutron reshapes our world is by revealing that stability is not the natural state of matter, but an achievement. Atoms do not exist because the universe prefers order. They exist because competing forces happen to balance. The neutron is central to this balance. Its presence shows that matter survives not through simplicity, but through compromise. Protons want to repel each other, the strong force wants to bind them, and the neutron allows both tendencies to coexist. This challenges the idea that the universe is built on single dominant principles. Instead, it is built on negotiation between opposing influences. The neutron also transforms our understanding of identity in matter. Elements are defined by their protons, yet their behavior, stability, and lifespan are often dictated by their neutrons. Two atoms can be chemically identical and yet behave very differently because of neutron differences. This reveals that identity in the physical world is layered. What something appears to be on the surface does not always reflect its deeper nature. In a broader philosophical sense, the neutron teaches that essence is not always determined by the most visible feature. Hidden components can be just as decisive. By studying neutron behavior, scientists have also learned that matter is inseparable from energy. The famous equivalence between mass and energy becomes tangible when nuclear processes are examined. Neutrons play a direct role in converting tiny amounts of mass into vast quantities of energy. This realization forces a shift in perspective. Matter is no longer a passive substance occupying space. It is condensed energy, structured and restrained by forces. The neutron sits at the heart of this restraint, holding energy in place or releasing it under the right conditions. Understanding this changes how we think about everything from the lifespan of stars to the potential of future technologies. The neutron further reshapes our cosmic perspective by connecting the smallest scales to the largest. The same particle that stabilizes an atom also determines the behavior of neutron stars, some of the densest objects in the universe. This continuity across scales is deeply unsettling and deeply beautiful. It suggests that the universe is not divided into separate realms of the small and the large, but governed by the same principles throughout. By understanding the neutron, we see that the laws shaping our bodies are the same laws shaping collapsing stars billions of light years away. Another shift in world view comes from the neutron's relationship with time. Nuclear processes involving neutrons occur on timescales ranging from fractions of a second to billions of years. Radioactive decay provides clocks that allow us to measure the age of rocks, planets, and the universe itself. These clocks work because neutron-related processes are remarkably consistent. This teaches us that time is written into matter. Atoms carry within them a record of cosmic history, and neutrons are part of the mechanism that preserves that record. Understanding this deepens our sense of connection to the past, grounding human history within a far older and grander timeline. The neutron also challenges the idea that power must be destructive. While nuclear weapons have cemented the neutron's association with devastation in the public imagination, this is only one aspect of its influence. The same processes that enable destruction also enable life. Radioactive decay warms planetary interiors, fusion powered by neutron-related reactions light stars, and stable nuclei make chemistry possible. This duality forces a more mature understanding of power as something morally neutral, shaped by context and use. The neutron does not choose outcomes, it provides possibilities. As our understanding deepens, the neutron becomes a symbol of scientific humility. It reminds us that even seemingly simple particles can hide profound complexity. Despite decades of research, questions about neutron structure, lifetime, and behavior under extreme conditions remain open. This uncertainty is not a failure of science, but a testament to the depth of reality. Each answer reveals new questions, pushing the boundaries of knowledge further. The neutron stands as a reminder that understanding the universe is not about reaching a final conclusion, but about continuously refining our picture of how things work. In a documentary sense, the story of the neutron is the story of a perspective shift. It moves us away from a surface-level understanding of the world and toward a deeper appreciation of unseen mechanisms. It teaches that neutrality can be powerful, that invisibility does not imply insignificance, and that stability is something earned rather than given. Through the neutron, we learn that the universe is not held together by obvious forces alone, but by subtle interactions operating beyond our senses. Ultimately, understanding the neutron reshapes how we see ourselves within the universe. We are not separate from cosmic processes, we are their outcome. The atoms in our bodies were stabilized by neutrons forged in ancient stars. The energy that warms our planet and lights the heavens follows paths defined by neutron behavior. By grasping this, the boundary between human experience and cosmic history dissolves. We come to see ourselves as part of a continuous story written in matter and energy. The neutron, uncharged and easily overlooked, becomes a guide to this deeper vision of reality. It reveals that the universe is not built from what is most visible, but from what is most essential. In learning to see the neutron's role, we learn to see the universe more honestly, more humbly, and more completely.